Welcome everyone. So, I am Presh and I am a teaching assistant in the course Digital Circuits which you are taking on NPTEL, which is taught by Professor Shantanu Chattopadhyay. So, this is our fifth session, fifth TA session that I am taking, and I will be covering logic gates as I failed to do it in our last session. So, as you guys are aware, and you are probably even more advanced than what I am covering. So till now we have covered introduction, number systems, in which we studied about different number systems, and then Boolean algebra, some basic properties over it. In combinational functional minimization, we spent a good amount of time in it, and we learned about how to minimize the functions using K-map and how to apply Boolean identities and why K-map are a better thing to use. Then we arrived on the logic gates, and we will be starting with logic gates in this session. So as we were discussing in the last session, I think some of you were there in that session, which got disrupted. So there are two basic type of logic gates. So one can be termed as basic gates, and other will be derived gates. So basic gates are your and or and not functions, and buffer gates are also there, and also inverter which is given by not. So in among these, I have drawn some symbols here. So this is AND gate symbol. This is OR gate symbol, but I was unable to get the exact one in the PowerPoint. So this is actually the OR gate. Then this is our inverter or NOT gate. And apart from knowing which is which gate, we should be also aware what are its truth tables and all, and how and what function does it apply on your Boolean functions. So for AND operation, for a two variable truth table, for AND or and not, and for not, we will take the input to be only A. So let me write down the inputs that we will be taking. Here we will be taking only A. So at output of AND, we should be getting A dot B. At OR, it will be A plus B, and as the output of inverter, we will be getting A complemented. So for a two variable, we'll just write down the possible cases. Then we will apply our, then we will see how the truth table looks like. So for AND function, it is very straightforward. Whenever your both of the inputs will be 1, then and then only we will be getting an output to be true or 1, or in other all three cases, it will be 0. And this will extend to even higher number of variables if you start to add here. Only when all of the variables are 1, then you will be getting a output to be true when all are 1. And synonymously with OR gate, you will be getting true output whenever even one of the output is true, or else this A plus B, as in case of our binary addition also, you will be knowing your output will be 1 only, will be 0 only when all of the inputs are 0. So in this case, your truth table will be looking something like this. And for not, we will be taking the input to be A. So this will just simply flip the input that you are giving to this gate. And I'm writing this 4 times because we have these inputs as 4 times. So these are the basic gates. So for realization of any logic circuits or any function using digital circuits, these three basic gates should be there and we are good to go to realize any logic hardware wise. Apart from these three basic gates, there are something known as universal gates and special gates. So in universal gates, we get two gates, NAND and NOR. So NAND and NOR are the gates, but they are called universal gates because you can use these gates to realize any of the basic logic gates. So our basic logic gates, as it is already written, are AND, OR, and NOT. And in next slide, I have just put up a basic schematic in which you can use your NAND and NOR gate to convert it to any of the basic gates. So that also we will see. And the truth table for NAND and NOR. So NAND is basically a combination of and NOT function, and synonymously NOR is combination of OR and NOT. So our this is a schematic for this is not NAND. So in NAND gate, simply the AND gate and a bubble function is applied. So this bubble is nothing but an inverter. So AND becomes NAND and its output becomes barred of A dot B. And in case of NOR, its proper symbol is something like this. A bubble will be coming and your output will look something like A plus B whole complemented or whole barred. So a short truth table we can write for two variables. So all the possible input cases, this we can write down. And for NAND, whatever we had in AND function, simply just flip it because it is A dot B bar as opposed to what AND was, which was A dot B. So here in this case, you will get a 0 when all of the inputs are true or 1. And in all other cases, you will be getting a true output or 1. And similar to that, in a NOR function, which is a complement of OR, a barred of A plus B, here you will be getting a 1 when all of the inputs are 0. And in the rest of the cases, you will be getting a false or 0. So this is a truth table for NAND NOR for two variables. And apart from that, we have XOR and XNOR. So this is also given by, this is also written as XOR as opposed to EX-OR or XNOR. So this is a symbol for XOR and this is for XNOR. And the operation for a XOR is written as A circled plus B. And this we can define in our in algebraic form as A complemented B plus AB complemented. And since we also have XNOR, so the expansion for XNOR is simply a barred form of A circled plus B, which will be giving A dash plus A dash B plus AB dash whole complemented. And the truth table for exclusive OR would look something like this. Even we will include XNOR here. So for two variable, all the possible inputs are this. And also, as the name suggests, the exclusive OR gives an output to be true only when one of the inputs is 1. And if both the inputs are same, it will be just be giving a false output or 0 output. So this will be the truth table for XOR, and just flip it and it will be a truth table for XNOR. Okay, so these are all the logic gates that are to be known. Now coming forward to universal gates, so we had NAND and NOR as universal gates, and in this whole schematic I have just used this space to explain the realization of all the basic gates using NAND and NOR both. So you might be seeing this slashed written. So whenever you are getting this first slash combination will be giving the output for the first slash. So when you replace these boxes by only NAND gates, you will be getting an AND here. So inverter is pretty much straightforward in this case. So you just have to short all the inputs and it will work for both NAND and NOR, and you will be getting an output to be an inverted form of what you gave as input. In case of NAND and NOR, so let's take NAND first. So if you take a NAND, I think you guys will be pretty much rehearsed in this. Yeah, so just let me know if this concept is well understood. So I will just move past it. And as you know, the output for AND should be A dot B, and in case of OR, you should be getting A plus B. Correct. And similarly, if you use a NAND gate and you want to realize an OR gate using NAND, so this will be the form that we will be using to convert NAND to OR. And as I discussed earlier, if you take NOR gates, you will be getting this second output. So I will just encircle the second combo. So when you take all the NOR gates, you will be getting the OR functionality in this combination and functionality in this combination. Okay. So this is the reason why these are known as universal gates. And also, I have just drawn basic gates at this point. You can also realize XOR gates, and also NAND to NOR conversion is possible. For that, in this stage where you are getting this output, um, there a NAND to NOR conversion is a 4-gate realization. So NAND to NOR or NOR to NAND, that is a 4-gate realization. So just keep these things in mind. Since these are universal gates, you should be aware how many gates are required to realize what function. So this is something which can be asked directly to you guys in competitive exams as well. So just be aware of the numbers which are required to convert gates from one to another. Then last time we were discussing something um, on logic families. So logic family which you have to choose depends on various factors. Correct. So in this schematic which I have taken from this website, Electric Veda, so there they have very precisely given the families. So I will just go ahead and I would ask what is unipolar and bipolar? So logic gate families are divided among unipolar and bipolar. So can you tell me why these are unipolar and bipolar?
It depends on the number of carriers.
Number of carriers. Okay. Anyone else?
That means MOSFET is a single unipolar carrier and
The
BJT is a bipolar carrier families.
Okay, but as you can see here, under unipolar you have PMOS, NMOS, which are single carrier, but in CMOS these both are included. So does that definition hold there about
Yes, sir.
single carrier? How?
So unipolar in the sense either holes or electrons has been present. Bipolar in the sense both the holes and electrons has been present.
Yeah, so that is true. So here, even though CMOS is a combination of both NMOS and PMOS, which are opposite carriers. So NMOS has N type and PMOS has P type. But again, in single device, there will be a single majority carrier. And also, since there is a single majority carrier, this means you can control this using a single kind of voltage level, which can span from 0 to positive or 0 to negative. Since you have only one kind of carrier, so you just need a one polarity of voltage to control. So this is also an alternative thing that might be asked at some places, depending on voltages. And in case of bipolar, as you guys pointed out, bipolar will be having both types of carriers. Can you mute Padmavati? Both types of carriers will be there. So here you might be requiring a voltage waveform of this kind, which spans from positive to negative, and depending on the biasness towards N or P type, you might be having some offset or at 0 volts. So these will be bipolar families. And the choice of family that this logic gate family that you want to use in your application depends on the number of inputs required, number of outputs that are to be driven using this circuit, then what kind of tolerance of noise margin is available to your application, then what kind of switching speed is required. These are some of the factors which you will look upon to select out of these families, out of all the available families for making a digital circuit. Also, there are two type of logic circuits. Either they can be combinational or sequential. So, I hope you guys are aware about combinational and sequential. Can you let me know what is a sequential logic? Just in short, either you can type or unmute and say.
In sequential, the present output depends upon the previous one.
Yeah, not only previous, it can be multiple previous outputs. And in combinational, whatever the output is there, it will be dependent on the current state of all the inputs. So, sequential logic, you get a factor of time there. So it is dependent on time, and this is time invariable, combinational. So time variability is something which separates these. So these two circuits, if you just use for a one-time logic operation, they will be giving us same output. But if you go with a pulsed input or something in which your inputs will be changing with time, and you want to get a time dependent output, so there you have to go with sequential logic. So these are two types of circuits that we will be getting to in depth in coming session, and I think you guys are already covering that in the course that professor is teaching. So now we know that we have our basic gates, we have some universal gates to realize these logic functions. Now the most common kind of realization is a two-level realization. Might I ask why this is a two-level realization and why is it popular? So I have already written in this slide, but I want to hear it from you guys. So why a two-level logic realization is quite popular? I hope you guys got my question, or else I have typed it down. So answer is here only. SOP and POS. Okay, so I will just move on forward with that. So, as the name suggests, it's a two-level realization. So you have two levels of gates. So let's say if you choose and or kind of two-level realization. So two-level means you have to choose two gates, and here NOT gate is not counted. So NOT you can freely use anywhere, NOT and buffer, or you can use or and there are other families, other kind of combinations also. But these two are quite popular, and or and because of SOP and POS format. So as you remember, your K-map output you would be getting either in SOP or POS kind of form, right? So in SOP, a sample function would look like sum of products. So you would be getting something in sum which was overall in a product. So sum of product is if you go from their implementation of and or, so and is nothing but a dot b kind of operations and or is a plus b kind of operations. So in a sum of product you will be getting outputs of or gates, numerous or gates, and at the final stage you will be getting a all of these outputs will be going as an input to your final AND gate. So this would look something like this. So there will be numerous of OR gates and all of its output will be clubbed together and that will go to an AND gate. So this is level 1 and this is your second level. And since you have used KMap extensively to simplify, in which you will be getting every min term to be a combination of all the variables that you are using in your problem. So if there are multiple variables, there will be multiple variable lines running, and you will be just combining the required inputs to OR gates, and then that output will be going to your final AND gate. So that's why two-level realization is very popular, because all of these functions that you have studied, which you have minimized, that are very easily implementable using this two-level realization. Similarly, POS can be implemented using AND and OR, as this I have discussed. So combination of ANDs, and this plus denotes the final OR gate. So there will be combination of ANDs, and this all will be giving a POS form, product of sum. So that is the reason why you have to be aware of two-level realization. So I have not included something in these slides, but I am expecting that you guys would have followed from whatever the professor is teaching. Can you tell me what is degenerate realization? This is related to two-level realization. Yeah, anyone? Somebody would like to chip in? Okay, so I will move on forward with this. So in a degenerate realization, for two-level realization, we always take our basic gates and OR, and also include our universal gates NAND, NOR in this mix, and NOT gate is used wherever it is required. It is not counted as a separate gate. So for two-level realization, these four gates are enough, and even if you use other XOR and XNOR gates, so that will again add on to this. But just starting with these four gates, you will be having a two-level logic combination of 2 to power 4, that is 16 kind of two-level realizations you will be getting, right? So these will include and or and NAND and NOR. So similarly, if you just take all the first one and then club it with other remaining four, you'll be getting some 16 combinations. Out of these 16, 8 are degenerate and 8 are non-degenerate. What that means is the degenerate combinations will be essentially doing operation of a single gate. So output that we can get using a single gate. So those all combinations are degenerate combinations. So out of these 16 combinations, 8 will be degenerate. And this is something that you should be aware, because these questions can be directly asked. I have also put one question in these slides, so we will go through that. Like the combination of and can be simply accomplished with one single and. So this is one example. So these are degenerate realizations, and these just increase the number of count of gates, and essentially they perform operation of only one gate. Okay, so this was two-level realization. Now I will be discussing only one of the families in particular. So as we have seen in our previous slide that there are numerous number of families, A, B, these if we number them, there will be n number of families that are available to choose from. But the most popular one these days that we use are MOS-based families. So, MOS-based families that we have seen in the classification of unipolar. And this is mostly technologically made possible because these can be just compressed down to a very small space, and this will be giving you a very large number of digital circuit realizations using MOS-based circuits. So even in MOS, you have NMOS, PMOS, these two kinds of independent MOSFETs that will be used, and CMOS is nothing but just a combination of an NMOS and a PMOS. And also I will just ask you, so if you make a circuit using NMOSes, what is this logic called? So what are the logic called using NMOS and PMOS? You would be aware if you had already gone through CMOS. So this is just one schematic of inverter, but actually you can just in numerous combinations of NMOS and PMOS, you can implement various your digital functions, and using PMOS family and using NMOS family independently also you can get same output as that you are getting in CMOS. So what are NMOS and PMOS logic implementations down? Yeah, quickly, anyone? I am audible, right? Anyone? Komal, you want to contribute? Okay, so if you use just a combination of PMOSes, you will be getting something known as pull-up network. And if you use only NMOSes, you will be getting something known as pull-down network. And a combination that we use in CMOS, all of the gates or realization that are below this common output line from which you are getting obtaining your output, all of the things which are below this, these are a part of pull-down network, and whichever is used implemented using PMOS, these are pull-up networks. So these are terminologies you guys should just be aware of and also keep in practice because these are directly asked and you should not get stuck in the wordings and these nomenclatures. So whatever you implement using PMOS is a pull-up network, and whatever you implement using NMOSes, that is a pull-down network, and that is related to the output being latched to something. So in case of PMOS, if all of the gates, all of these transistors are made on, this output is actually just pulled up to the level of VDD, or here VDD is 1 and ground is 0. So if all of the PMOS logics are giving an output to be true or they are just turning on, at that point your output will be 1 and it will be just pulled up to the level of your VDD. And in case of NMOSes, if all of these become true, then your output is just pulled down to ground. So that is one basic nomenclature that is used. Now let's get into some of the practice questions that I have gathered for this week. Now, which of the following is a degenerate implementation? So degenerate I was not planning to discuss in the slides, rather on this question, but since I have already told you what is a degenerate logic realization, just take an attempt on this question. So I have given four options. Out of these, which one is a degenerate implementation? And I will just go on. Yeah, Janapriya?
And
And or. Yeah, so as I was saying, there is not only one option which is true for this, and I am asking which is a degenerate implementation. Okay, so one is pretty straightforward here, the D option or. So this is a degenerate implementation which will be giving us functionality of one or. Then NAND NOR is a one combination which is a degenerate combination, and NAND is also something which gives degenerate implementation. So these three options are actually the ones which are giving degenerate combinations, whereas and or is a two-level implementation which is a non-degenerate one. Also, and or is something that you use for some of this product of some kind of implementation. So here three of these options are giving degenerate implementations. So I would just say go through this part carefully because this is not something which is mathematically intensive, but this is something which is directly asked, just like this.
Hello.
Yes, Komal.
So which option is correct? I mean,
So
you said
here,
that and is also gate of the degenerate implementation. So what about?
sorry,
Can, can you repeat this? I mean, you said that all combinations are correct. Means above three
no.
combinations
So
are correct for what?
yeah, these are degenerate implementations. So in question, I had asked which of the following is a degenerate implementation, right? So only the option B is a non-degenerate implementation, whereas the other three A, C, D are actually degenerate implementation. So there were multiple answers to this question. So that's why you have to check every option and not just jump on the first one that you see.
Okay.
And I hope this degenerate, non-degenerate, something that you just practice it. So there are 16 combinations. You just by heart the 8 combinations which are non-degenerate and 8 which are degenerate. So these are just directly asked questions. Then, which of the following could be output of a sequential logic function? So, as you guys are all aware, what is combinational and sequential. So, just by looking at the given possible functions, let's say these are just a stage of something, some large function. So, this output might be going to something else, and this might be coming from something else. So, this f, which is given in the options, which of the following could be output of a sequential logic function? This one should also not be a problem for you guys. You can punch in your answers in chat also. And also, these are related to some gates. So while you guys are taking a guess, I will just write down the corresponding gates. Nobody. C. Sanjay is saying C. Okay, so I think others are not able to type in time. So here C is something which can be a output of a sequential logic function. So here in this case in C, you have a condition written here. I think this is visible. This is a bit small text, but there is a time dependency to the output. So I will just write down this in a bit big letters. So here the f is defined as a, which is 0 when t is even, and 1 when your t is odd. This is just plus with B. So that's why the output is or slash B. So whenever this is at t even, you will be getting an OR functionality, and when the t is odd, you will be getting output to be just B. So since there is a component of time related to this option, so this one can be an output of a sequential logic, a sequential function, whereas the others are just combinatorial functions which are giving and time invariant output. These are just AND gate, OR gate, and XNOR gates. But this C, depending on the time instance at which you are taking the output, you are getting either OR gate or a B output directly. Oh, sorry, I just reversed it. Also, this is not just or B. It's bad on my part. We'll be getting just a B for T even or a 1 for T odd. So whenever this time dependency or time variance comes in your logic or even a single block, this would introduce the sequential nature of this implementation. Now moving on, I have not written down the options for this, but I would like you guys to type down the output of this logic implementation. So this is kind of two-level logic implementation, and also let me be clear, this is an bubbled OR. So I was unable to find the exact symbol for this. So this is a bubbled OR. This is an AND or not. This is a NAND. You can call this a NOR also. Fine. So just punch in the output that you will be getting. Meanwhile, I will be just writing down the outputs at various output lines as we go through the circuits from the input. So if we start with A, so A is getting into this top gate, and here you are getting an A. Then the second output, if we track it down, this goes to B. So at this point you are getting just A and B, and the output at this point is A dot B. And then moving on to B input, one of the B goes to AND that we have accounted for, then one of the input goes to your NOR gate. So there this B we can write down. Then C passes through an inverter. So initially you get a C, then you get a C complemented, and this C complemented goes to your NOR function, NOR or your bubble door. So these are interchangeable. So at this point, the NOR function is given as, this is just a complemented OR. So A plus B complemented or barred. So what we will be getting here will be B plus C dash whole barred. Okay, so this will be output at this NOR gate. Then these will be inputs to the final NAND gate. So this A dot B goes to one input of this NAND gate, and the other is B plus C dash, and this goes into NAND gate. And for NAND, we know the two input NAND has this output A dot B barred. So over these two inputs, which is A dot B, we can just put them in brackets for now, and B plus C bar. This is already barred. Sorry, it's a single bar. Fine. And this is ANDed, and then a complement is kept over it. So this is what we are getting at this output. Nobody has typed in. I hope these gate implementations are clear with you guys, right? Graphical.
Yes, sir. We also received the same answer, sir.
Okay, okay, you got the same. Nice. So this even you can go on further and simplify to get even a simpler form. So let's minimize, and then you type down the answer that you are getting. So just minimize this or get it to a simpler form by removing these bars and then get me the final answer. So let's do that. So let's keep the outside bar as it is, or else we can just use that outside bar. As we have solved some problems, we know that this whole bar or this whole complement we can distribute among these inputs that we are having. And then this dot will become plus and complement gets distributed. So using that, this will be A dot B complemented plus B plus C complement. This is already a whole bar, so this I'm just writing as a complement. And one more complement will be coming because of the bar that we are having at the start. And just leave this like this, A dot B. Then this complement and complement just cancels out each other. Then you will be left with B plus C complement. Furthermore, this complement we can bring inside this A dot B operation. Then you will be getting A complement plus B complement plus B plus C complement. Rosalind has typed in some answer. Okay. Okay, this can further be simplified, Rosalind. As you can see here, we have a B plus B bar also. So B plus B bar would just this will be nothing but if you take B to be 1, this will be 1 plus 0, and if you take B to be 0, this will be 0 plus 1. So this will be always giving out an output to be 1. Correct. So A complemented plus C complemented plus 1 you are getting, and this 1 will make everything to be true. So the output will be actually always 1 for this function, what we have written. For this FABC, we'll be getting 1. Yeah, you also write the same thing. So what we'll be getting is 1 if we simplify this. So from this graphical implementation also, you should know how to get back to our initially minimized function that you are supposed to implement. Also the reverse process that you guys are already practicing. So first you are just minimizing and then using this logic gate implementation. I hope you all got understood why we are getting 1. You all understood, right? Now, since I have discussed multiple times about sequential, so I just took a liberty to introduce the time component here in this question. So this is not exactly a sequential circuit. Sequential circuit will be actually having some more components to it, which I hope you guys are already covering, which I will include in my next session. So this is just a simple sequential circuit, and you guys have to type down the outputs at G1, G2. Okay, so I have not mentioned G1, G2. So G1 is this point and G2 is this point. Okay, so at G1 and G2 at t equal to 4. So this is the pulsed input that you are giving to ABC, and at instance 4. What will be the output that you will be getting at G1 and G2? And also we will just go forward and we will see what will be the final output. So any direct guesses? So I hope this circuit is I think already known to you guys. The circuit which is drawn here. Yeah, so any guesses for the okay, the final answer, I hope you guys already know that this will be 1 because this is the previous circuit that we that I have just used here. And for that we have seen the output is 1 always at this output. But I am asking to get outputs at G1 and G2 at time t equal to 4. So we will just go forward, and from last question we know that A dot B is actually G1 and B plus C complement bar is G2. So I will just pick it up from there and use it directly. But if you get this kind of question, then you should be able to write down the form which you are getting at different points of these circuits. This is also a very helpful thing in debugging. Whenever you debug these hardware circuits, this is very much needed. And this is B plus C complement, whole complemented. So Anil has typed in 1 and 0. Very good. So we will just get to see whether that is correct or not. So G1 at t equal to 4. So at time step equal to 4, you are having A to be 1, B to be 1, C to be 0. And now since we already have G1 and G2 written as functions, we can directly write it down. So G1 is A dot B, which is 1 dot 1, which gives out to 1. Then G2 is B plus C complemented, whole complemented. Now we already know the values for A, B and C. So for this, B is 1 plus C is 0. So C complement is 1, 1 plus 1, and this is whole complemented. So 1 plus 1 is 1, and 1 complement you will be getting 0. So for G1, G2, this will be 1 and 0. So yeah, Anil, you are correct. And invariably, this output will always be 1, as we have seen from the circuit that we solved just before this question.
Sir, A is equal to 1, B is equal to 1, and C is equal to 0. We have taken from this
From,
pulse diagram.
yeah, this pulse diagram I have provided here. So at time t equal to 4, these were the states of the inputs. So from there we picked it
Okay.
up. So this is not exactly a sequential circuit per se, but there is only a time variance factor included. So, but in sequential circuits, when the input, there's outputs and inputs are dependent on the previous states of your circuit, at that point of time, you should always be knowing what are the functions that you are getting at different nodes of your circuit. Also for debugging purposes, also to understand how your circuit is functioning and whether it's correct or not. So in case you go on designing a logic or a sequential function, you should be knowing that. Then this is a straightforward question which is directly asked in some competitive exams. So how many NAND gates are required to realize NOR, and XOR gates? So in these four options, there are three numbers each for every option, and this is a straightforward one, but you should be knowing the theory behind it. So that I have not discussed because this is discussed to a great length in the course that professor is teaching.
Option A. Option A.
So Komal is saying option A. Um, Others can also punch in the answers. So NAND to NOR, also in the generalized form where I had just written down that circuit. This takes four gates. Then NAND to AND simply takes two gates. That is one NAND, and other NAND is just used to invert it. And then XOR gate.
So
Yeah, so this takes five gates. So 4 to 5 is correct answer. And I have not included the figures to this implementation, but so here a NAND to NOR, simply one more block is added here to convert the functionality from either NOR to NAND or NAND to NOR in this block diagram. So this overall function will become NOR slash NAND. And XOR takes 5 gates, so that I have not included in this, but you should explore it. And in the next session, I will include that figure directly. So always just keep in mind how many gates are required for what, because these are universal gates. So at least the number of gates should be known, if not the circuit. And we also discussed to some extent about different logic families. So, CMOS family is something that is discussed to great extent, and also this is the most popular one. So we know CMOS family, we know it can be used to implement gates, but what are the gates that we can implement using CMOS family? Can you let me know? So either in these options as we see, NAND, inverter, XOR, NAND, NOR, inverter, or AND and OR. So which combination of gates are implementable using a CMOS transistor family? Anil is saying C.
Inverter.
What?
NAND nor inverter.
Okay,
Option C.
so okay. So yeah, C is the correct answer. So using CMOS family as we have seen in this figure, which is just an schematic for an inverter. What's happening? Okay, it's not getting erased. So this is just a schematic for inverter. So using only these one gate each of NMOS and PMOS kind of device, you can get one inverter. So inverter is pretty much straightforward that you can implement. But as you can see, the output that we take is from this point, which is a combination of pull-up network and a pull-down network. So what happens in this case is that you cannot directly implement AND and OR gates. So and OR, these basic logic gates are not implementable using CMOS. Rather, you get NAND, NOR, and inverter. So using NAND and NOR, these are universal gates. You can always implement AND, OR, and whatever combination you require, like XOR, XNOR, and inverter also you already have. So this CMOS family can be used to implement these three gates. And apart from using these three gates, we can implement any combination in CMOS. So that was all in this session. I hope this session was helpful in the course for you guys that you are going through. Can you let me know where Professor has reached? So I think I'm lagging by 1 week now. Can anyone just unmute and tell
Yes,
me?
sir. Yes, sir. Actually, I have doubt in assignment number 6 already submitted and date is also over.
Okay.
So you are, I mean, you are lagging. You said you are lagging.
Yeah,
I mean,
so
because
last week I
marks
could not
and
take
other
the
things.
class. Yeah. So
Yeah.
you had doubt
So,
in one question, right?
yeah, in assignment number, yeah, about the marks itself.
What is the question? So I
Sir,
don't
I have
have
to
these
go through.
assignments. Okay, okay, fine. You can just mail me that question. So I don't think we TAs have got the assignment questions with us. You can just mail the question to me. We'll see.
All right.
Yeah. So till what part professor has covered? Hello.
Sir, uh, sir, sorry, I haven't gone last week. I mean, seventh week topic, but
Okay.
till six, means I attended all the lectures. That sequential.
Sequential circuits. Okay. Okay, the sequential has been covered. Okay, fine. So I will get in that same pace. Sequential asymmetric machines. Okay, fine. So I hope I will be able to cover that in next session. So these basic adders, multiplexers, and those things are already covered. That I understand. Okay, so I will bring this session to close. And whatever doubts for submitted assignments, you can directly mail me on this mail ID. I will check and try to solve and get back with solutions to you guys. And yeah, thanks for attending.
Thank you, sir.
I failed to submit weekly assignments because of what to submit. Okay, Kavita, I will check with professor. Do you guys have some roll number or something? Or directly by name I can ask him. Yes, Sufal, we put these videos on our respective YouTube channels. So, uh, okay, I will share the link address in upcoming sessions.